So, hi everyone. My name is Dr. Destenie Nock, and I am going to be presenting on the more social good side and prescriptive analysis that I have been developing. So, my work is focused on energy planning, and I look at both the US and in developing countries, but this talk is going to be focused on developing countries. So this is really motivated by Sustainability Goal 7, where we're going to try to help ensure universal access to affordable, reliable, and sustainable energy for all. And so when we are thinking about the situation in the developed world, we see that the grid is very well developed and access to electricity is unlimited and the system is considered to be reliable. And so the problem becomes minimizing costs subject to demand, reliability, and environmental constraints. But in the developing world, the situation is almost flipped on its head because access is very limited and the system is considered to be unreliable, meaning that there might be hours of outage per day and that the demand is often unknown. So then this engineering problem becomes maximizing social benefit subject to a cost. And so when I'm thinking of social benefit, I'm really using the Human Development Index as a way to estimate the social benefits that you might see countries gain from increased electricity consumption. So the Human Development Index is developed by the United Nations, and it's a composite statistic of life expectancy, education, and per capita income. And so in the graph in front of you, you see the Human Development Index on the y-axis, the per capita electricity consumption on the x-axis, and each data point is a different country. And so we can see that while we're not saying that this is a causation, we see a very strong correlation between the different countries and increasing electricity consumption. And we see that we get decreasing returns to scale, so it looks more like a logarithmic curve. So when we are integrating this into our optimization function, we developed the Maximize Energy Access model. And this is really going to have a different objective function from the least cost models, which look at minimizing costs subject to demand constraints. And here we're saying we want to maximize a stakeholder's utility based on the associated happiness they get from increasing electricity access. So the utility function U of XP, so XI is the maximum electrical energy that can be delivered to node I, and PI is the population within that node. And we can see that the utility is going to be a function of the per capita electricity consumption in each node, and we raise that to a 1 minus alpha, where we're calling alpha the equality parameter. So this is how much the stakeholder cares about the distribution of electricity around the country. So if it's a 1, if alpha is 1, then we say that they care a ton about equality and they want to make sure that everybody has equal access. And then if they don't care at all, that's alpha equals 0. They only care about maximizing the total electricity in the region. So I don't have time to go through all the constraints in the optimization model, but this is a flow of information within the model. So we have the inputs on the left, which are the social planner's preference for equity, the budget and geography constraints. And then in the dotted box, we have the me model, which the highlighted boxes, the orange boxes, show what is actually calculated endogenously in the model. What decision variables are decided within the model. So we have generation investment and transmission investment. These flow down into a power flow calculation. Then it does the electricity consumption decision. And this runs up into our budget constraint set for the country. And the electricity consumption also feeds into our objective function, which is the overall social welfare of the country, which is determined based on the stakeholders' preference for utility of electricity access. Okay, our initial case study was Liberia, and we chose this country because at the start of the study, Liberia was very limited in their electricity access. Approximately 5% of the country was connected to the Liberian Electricity Corporation, or their main centralized grid. 81% had absolutely no access, and then the other people that did have electricity access were off-grid, and they shared some form of generator or battery. And then on the left, we see a population density map of Liberia. And we can see that most of the country lives in the northern part, and there's a few population centers in the south of the country. So this is an output from the model. So these are recommended electrification plans based on different equality preferences of those stakeholders. So for these maps are for a budget of $10 million per year annually for 30 years. And we see on the left, this is our low equality preference of alpha equals 0.1. And we can see that the model is recommending to use the existing centralized facilities, the hydro plant in blue and the oil plant in gray, but it's left a large majority of the country unconnected, which is actually similar to what we see right now. If we change this over to our high equality preference case, then we see that the strategy for using the existing hydro plant is similar. It's recommended to do that, but it has recommended not using the existing oil plant due to high fuel costs and uncertainty there. And it's recommending to build out the low voltage transmission infrastructure, but also invest in PV diesel mini grids, which are those yellow diamonds. And then if we increase this budget by a factor of 5, we can see how the electrification strategy changes, and that we see that the main trade-off between high and low quality preferences is investment in transmission line infrastructure. But we see that there are large centralized power plants as the main electrification strategy in both cases. But in the high quality preference case, we are seeing more incentive to invest in transmission line infrastructure. So then just to kind of give you a brief overview of the sustainability trade-offs that we're seeing between the different electrification strategies. So in the graph, the blue represents the colors represent different budgets, and the solid lines represent the high equality preference, and the dotted lines represent the low equality preference. So we can see one of the main things that we see here is that neither equality preferences nor budget has much of an impact on water greenhouse gas emissions. It's only when you're in that very low budget case, the 10 million seen by the blue, that you get some big trade-off. And this is because there's a large investment in PV diesel mini grids, which we probably wouldn't see if we had allowed the system to build PV battery mini grids or just PV standalone mini grids by themselves. And so I got a time warning, so I'll just wrap up quickly. I saw some opportunities for collaboration with artificial and machine learning opportunities. One would be to help prevent and predict electricity theft, but also predicting demand over time. Demand is very difficult to predict in these models because people currently don't have much access. Then I can talk more about these if anybody wants to. And overall conclusions, my model determines generation expansion plans under different stakeholder preferences for equality. And we can use this information to make better investment decisions and more equitable decisions. And then this is my contact information. So thank you very much.
Thank you, Destiny. So any questions from the audience? Okay, I have a quick question. So you mentioned that we can potentially use AI or machine learning. So what kind of data is available there that could potentially be used for predicting the electricity theft?
So there is some data on like previous mini grid use. There's a lot of mini grid developers within the country. So looking at how people have actually changed their use over time once having these mini grids, and you can kind of think about how different pricing structures has incentivized different demand patterns. Mm-hmm. So that would be one source of data there.
Cool. Thank you very much.